Okay, so we're going to take a look at some physics challenge questions on waves and optics. We're going to start off looking at a ripple tank and a stroboscope. So let's break this question down into more manageable chunks. So to start with, we've got a ripple tank at 20 Hertz, and the waves travel at a speed of 40 centimeters per second through a gap in a barrier of width 1 centimeter. Calculate the wavelength. So the key is going to be these units. We have to pay attention to them. They're in centimeters. So first of all, let's calculate the wavelength, converting the speed into meters per second before we use the equation. So we've got a wavelength of 2 centimeters, which you would notice is just a little bit bigger than the gap we've got. So if the wavelength is slightly bigger than the barrier width, what we're going to get is some diffraction. And some things to have in our sketches. So with a gap that's less than the wavelength, but that they're a similar size, we'd expect to see the wavelength unaffected. So the distance between the wavefronts should be about the same. And we'd expect to get semicircular wavefronts like you can see. If the gap is made now 4 centimeters, what we'd expect to see, because we've now got a gap greater than the wavelength, so the waves that go through the middle should be unaffected, so they should stay pretty straight, and then we'd have curves at the edges. Okay. So a handheld stroboscope is used to observe the experiment. You might have used one of these. It's basically a giant circular wheel with some holes in it, so you can observe periodically. So this one is a disc with 10 slits in it. Each is equally spaced around the circumference. If you observe the waves through the rotating disc, you'll see them several times a second. Explain why the waves look stationary under a stroboscope rotating at 2 Hertz. So first of all, if the frequency is 2 Hertz and there are 10 slits, that means 20 slits are going to pass in front of your eyes every second. And you'll also note that the frequency of the wave is 20 Hertz. So every time a gap goes in front of your eyes, you're going to be looking at exactly the same point on a wave. And that's why it's going to appear like it's not moving. Okay, so now describe what we'd see if we changed the stroboscope rotating frequency. So now it's 1 Hertz. So that means we're going to have 10 slits passing in front of your eyes every second, but we've got 20 cycles of the wave per second. So it's still going to look stationary because you're still going to see the same point on the wave each time, but you're going to miss one. So let's say we're looking at a peak. We would see a peak, we'd miss a peak, and the next time a slit came in front of our eyes, we'd see another peak again. So it still looks stationary. Okay, so then 4 Hertz, that means we're going to have 40 slits passing in front of our eyes per second. So what we're going to see here is alternating points on the wave. I'm going to see opposite points. So if the first slit comes past and we see a peak, the next time, half a time period is going to have occurred for the wave. So we're going to now see a trough, then we'd see a peak, then we'd see a trough, because it's going at twice the speed. Okay, so if it's going at 1.9 Hertz, that means we get 19 slits passing in front of our eyes per second, whereas the wave is 20 cycles per second. So what that means is the time between 2 slits, we're going to have just over a time period for the wave. Now what that means is if we started looking at peak, the wave will have gone down to a trough, up to a peak, and then started going back down again by the time the next slit comes past. And so it will appear like the wave is slightly traveling forwards because we've got a peak, then we've gone the bit just after the peak, and then we'd have a bit just later than that every time. So we're going to have it looking like it's traveling forwards. And then finally, suggest why in cinefilms wheels sometimes seem to rotate backwards on forward-moving vehicles. So what I've done is I've got a wheel and I flagged up one particular kind of spoke of the wheel. So a cinema or a movie shoot films at about 24 Hertz, which means they take 24 images every second, just fast enough that our eyes can't see that it's repeated images. So if we have the wheel such that it doesn't quite get to the next spoke in between two images. So what we're looking at here is basically one image followed by the next image. It's going to look to us watching it like the spoke has gone backwards. It hasn't actually, because all the spokes are identical. It's going to look like the spoke's gone slightly backwards, and it'll look like the wheel is rotating backwards on net, because we can't tell the difference between the spokes because they all look the same. Okay, so a submariner looks in a low mirror of a periscope, which is basically based on two mirrors. A fly has found its way between the mirrors and buzzing around, and the diagram shows the mirrors and the position of the fly. Indicate on the diagram the orientation and approximate position of the fly. So the key here is to know about mirror images. So remember, they are the same size as the object. They're an equal distance from the mirror as the object. They're imaginary type images, and they're laterally inverted. So this is where our image is going to be. Okay, so in terms of the arrows, so we can see the arrow A is going along parallel to the mirror, but away from it. So our image, it should be going along parallel, but away from the mirror. And B, we can see, is going sort of in towards the mirror, so our B should also be going in towards the mirror there. And those would be the directions there. Okay, so a ray of light with frequency 5 times 10 to the 14 Hertz is refracted from a vacuum into glass. So we're going to slow down, and we'll use that later on. Which is the correct row? So the first thing to use here is that during refraction, frequency doesn't change, and that speed and wavelength, therefore, must be directly proportional. So if speed decreases, so should the wavelength. So first of all, let's eliminate the two options which suggest frequency changes, because it doesn't. And when we go from a vacuum into glass, the speed should decrease, and so should the wavelength. So we can see that that leaves us just with option D. Okay, so a police officer directs a beam of radiation at a car. He detects a returning beam. The waves were. So here I can eliminate ultraviolet, gamma and X-rays, because those would be like ionizing, so we're obviously not going to use those in this situation. So we've got either radio waves or microwaves, but I would say radio waves would be quite unlikely to be reflected off the car, since they can get inside it to the radio. So I'm thinking we're going to be using microwaves here. So a girl stands 130 meters away from a high wall. She claps her hands together at a steady rate so that 37 claps are made in 30 seconds, starting at time equals 0, and they end at time 30. Each clap, except the first, coincides with the echo of the one before. Calculate the speed of sound. Okay, so first of all, the sound has traveled a distance of 260 meters if we're hearing the echo, because it's gone 130 and 130. And if the first clap is at t equals 0, we've had 36 claps in 30 seconds. So we can work out the time between claps. Once we know the distance and the time, we can work out the average speed. Okay, so the diagram shows a ray of light entering a glass block. Which statement is false? This one I picked up straight away. This one suggests the frequency changes, which it just doesn't, whereas all the others make complete sense for the situation going into something with higher refractive index. Okay, so we've got a diagram showing the idea behind a disc siren. It consists of a disc in which there are 16 equally spaced holes, all the same distance from the axle. When a jet of air is directed at the holes and the disc is rotated at a particular constant rate, the frequency produced is 320 Hertz. Calculate the frequency of the note produced when a disc containing 24 holes is rotated at 4/3 times the rate. So if we have more holes, we're going to get a higher frequency, and we can work out that ratio doing 24/16. And if we're spinning it at a higher frequency, that's going to give us a higher frequency sound too. And when we multiply those together, that gives us a scale factor of 2. So the frequency is going to be 640 Hertz. How does the sound of this note compare with the sound of the original note? Well, it's double the frequency, so it's going to be a higher pitch, and it's actually going to be exactly 1 octave higher if we've doubled the frequency. How is the sound actually produced by the siren? Well, we're getting pulsing of air because when there's a gap, air is allowed through, and when there's not a gap, air is stopped. So we're getting a pulsing of the air, and that's going to produce what we call a square wave because it's either going to be on or off. We're going to get nothing in between. So we're going to get a square sound wave. Okay, so ocean waves arrive at the beach roughly parallel to the shoreline, even if they were not travelling parallel to the shoreline when they were further out to sea. So this is a question about why waves change direction as they approach the beach. So we've got an equation to calculate the speed at a given depth in water, c equals root gd. Okay, so we've got an investigation where we've changed the depth and measured the time taken to travel the length of a ripple tank, and the length is 70 centimeters. Okay, so use these results to verify the speed equation is reasonable. Okay, so using this equation, we should be able to see that c squared is directly proportional to d once we squared both sides of this expression, because g is a constant. So if we calculate c squared over d, we should get a constant, and that value should be around 10 because it's g. So what I'm going to do is, in place of c, I'm going to put L over t because it's distance divided by time. So doing L squared over dt squared for the 3 sets of data, we can see we do indeed get a value of g around about 10. So I would say it's confirmed or verified that equation. Calculate the speed of water waves when the depth is 90 centimeters. So we basically just need to plug into the equation, but convert into meters, and that gives us a speed of 3 meters per second because that's root of 9. The diagram shows an idealized cross-section of area of water approaching a beach. The water gets shallower in the 3 steps and then ends at the beach. The waves travel from the left towards the beach. So essentially we're getting shallower and shallower in stages. Okay, so then in this question we're going to look at sort of how the wave front changes as it approaches the beach based on the fact that we're changing it in stages. Okay, so the wave is approaching the beach at an angle of 30 degrees. And as we cross from A to B, we're going to get refraction. And this equation you can see here is essentially a rearrangement of Snell's law that you probably haven't seen before. But the angles are still measured to the normal, just like in Snell's law, and we've got the 2 speeds there. On the diagram, indicate the direction the wave is travelling in region A, and the approximate direction the wave will be travelling in region B. So what we're going to have is the direction of motion is always perpendicular to the wavefront, so that one's fairly straightforward. And then I reckon we're going to get something along this line, so it's going to bend towards the normal as we cross into shallower water and slow down. Okay. Calculate the direction of the wave in region B. So we're essentially using the equation. So first of all, I'm going to calculate what sine B is using the values, and then using the fact that C is equal to root GD. And so I've substituted that in, cancelled the G's out because we don't need them. And then from that, we can calculate what sine B is, and therefore we can calculate what B is, 45 degrees, and we can see it has indeed bent towards the normal. Okay, the wave enters region A at a rate of 1 wave every 10 seconds. Determine the wavelength. Well, we know the speed in that section is 3 meters per second. And if there's 1 wave every 10 seconds, that means there's 0.1 waves in 1 second, or a frequency of 0.1, giving us a wavelength of 30 meters. Okay, so we're going to change this up. So previously we had stepped depth changes. Here we have gradual depth changes. So sketch the position and shape of the waves between the ones shown. So this time what we're going to get is, because it's gradually changing, we're going to get the wave slowly bending as it approaches the shoreline until most of it is parallel to the shoreline apart from the very end of the wave. So this time we're going to get gradual bending. So the final question is looking at an optical fiber, which we use to send information using light waves, essentially. So we've got an inner core of high refractive index and an outer layer of lower refractive index to make sure that total internal reflection can occur. But one of the issues with optical fibers is light can take multiple paths through them. And we're seeing there 2 paths, the shortest path and actually the longest path that we can take through. So again, we've got a statement of Snell's law, but this time using refractive index instead of speed. And it says the critical angle is when the angle of refraction is 90 degrees and the critical angle is the angle of incidence. So show the critical angle is 70 degrees. So I'm going to start with this form of Snell's law, n1 sine I equals n2 sine r. Sine r is equal to 1 because r equals 90, and then the angle of incidence is the critical angle. We take n1 to the other side, we plug the values in, and then we can calculate our speed, or critical angle, I should say, is 70 degrees. Okay, so we've got a 1 kilometer optical fiber, and we're trying to prove that the time difference between the two paths we've seen is 0.4 microseconds. So we've been given the diameter, and we know the speed of light, sketched the two paths, and that should in theory help us by figuring out the path difference. Okay, so here's my diagram, and we know the longest path is when it's just above the critical angle, and remember the critical angle was 70 degrees. So this angle here is going to be 20 degrees, and I'm going to use that. So the first stage I've used here is I figured out what the speed of light is inside the actual core, because the refractive index is 1.7. So we can see it's actually traveling slower than the speed of vacuum. So that's the first stage. And then what I did is I calculated how long it would take along the shortest possible path. So we've got the time for that. Then I'm looking at calculating the time for the longest path. So what I've done is I've calculated the component of velocity parallel to the 1000 meters. So if the speed is sort of an angle at 20 degrees, if I multiply that by cosine of 20, that calculates the speed parallel to the 1000 meters. And if I do 1000 divided by that, that tells me how long it takes to travel on that longer path. And if I find the difference between the two times, it does indeed come out around 0.4 microseconds. So the digital signal emerging from the end of the fiber is a combination of signals that are traveled along the two paths. When the on from path A arrives at the same time as an off from path B, the signal is lost. Calculate the maximum frequency. So the time period is going to be 2 times the difference, because if one is on and one is off, they are clearly half a time period apart because they're at opposite parts of the cycle. So that means the 3.6 times 10 to the minus 7 represents half a time period. So we times that by 2 to get a full time period. And once we've got a full time period, that allows us to calculate what the frequency is there. Okay. So then final question, state and explain how each of the following changes affects the maximum frequency that transmitted. Decreasing the diameter, well, that should have no effect because we haven't changed the critical angle, so we haven't changed the path difference or the time difference, so we should get a same time period, so same frequency. If we decrease the refractive index of the outer layer, so effectively we changed N2, if we decrease that, that has the effect of decreasing the critical angle. And if we decrease the critical angle, that increases the difference. Because if we go less than 70 degrees, that 20 degrees becomes bigger, essentially. So we increase the path difference, we increase the time difference, we increase the time period, therefore we decrease the maximum frequency. And that's the logic I used.